Welcome back. In the last session, we have seen the model training, but in this session, we'll see some advanced concepts on model training. So let's talk about the most important concept called early stopping, a method that can save you both compute time and improve the model accuracy. So if you can see that this early stopping really works well in iterative models, especially boosting based models like XGBoost. The core idea is very simple. Stop training your model once it stops improving on a validation set. So let's walk through how it works in each stage. In the beginning, your model is learning useful patterns from the data. If you are using something like XGBoost, that means adding one tree at a time, each one trying to correct the mistakes made by the previous tree. So here the model is in training phase and both the training and validation errors are decreasing. Everything is going well. So as the training continues, we monitor the performance of the model, like how is accuracy, F1 score, AUC and RMSE on a separate validation data set. This is crucial because the training errors might keep going down, but the validation error might start to level off or even go up, which is a red flag. Here is where the early stopping helps you. You specify something like early stopping is equal to 10, which tells the model if the validation metric hasn't improved for 10 rounds, stop training. The training halts automatically and the best model checkpoint, the one that had the best validation score, is retained. So in a customer churn model, a telecom firm, we trained say with early stopping of 74 rounds instead of 200. So that saved hours of unnecessary training and actually improved the real world performance of the model. So the model doesn't just stop there, it actually rolls back to the stage where it has encountered the best performance. So even if the last few rounds performed worse, the model used in the production is the one that gave us the best performance. So you can see that in the chart, the training error keeps decreasing, the model keeps getting better at memorizing the training data. But the validation errors start increasing after a point. That is a classic sign of overfitting. So early stopping helps us to catch that peak and then stop right there. So early stopping is good to have in your ML training, especially when using boosting models in the classification or regression task. It's easy to implement, prevent overfitting and saves time and often improves the generalization of the model. So use it with validation set and well chosen metrics, and this is really going to improve your outcome of your model. Now that we understand what early stopping is and why it matters, let's break down how it actually works step by step. This slide will walk us through a 5-stage process that happens behind the scenes when early stopping is implemented in models like XGBoost or even light GBM. Let's dive in. So the step number 1 is data splitting. We always begin by splitting our data set and not just training and test data, but training and validation sets. Why this is important? Because early stopping depends on validation metrics to decide when to stop. If we don't monitor the performance on unseen data, we'll have no idea when the model starts overfitting. So for example, in a chain prediction task, we might slip 70% for training and 30% for validation. The training data helps us the model learn. The validation data tells us when to stop. And then step 2, we do an incremental training. Next, the model start training incrementally. For the tree based model, this means adding one decision tree at a time. Each new tree attempts to fix the residual error from previous trees. We have seen an example of the XGBoost in the previous session. So this is the boosting philosophy, small steps in the right direction, layer by layer. So if you want to think like an example, think of a building a wall by stacking one brick at a time. After each layer, you assess whether the wall is still straight, if it's tilting, or you stop and reinforce, right? So then after every iteration, say every new tree, the model evaluates its performance on a validation data set. So we monitor metrics such as AUC for binary classification, RMSE for regression, log loss for multi-class classification. So this constant feedback loop is key. Without it, early stopping wouldn't know when to act. So once you have that, then next step is monitoring and termination. Now comes the key part of early stopping. We define the parameter early stopping round is equal to say 20. This means if there is no significant improvement on the validation metrics for 20 consecutive rounds, stop training. It's like saying, we have monitored it for so many rounds, there is not much is improving, let's call the for the day, and then we are stopping training. So the reason is this step saves you from running instead of say 500 rounds to say maybe around 100 rounds or 150 rounds or 200 rounds, right? It saves you both your compute time, also that model training time. So finally, after termination, the algorithm doesn't just return the latest last model, it returns the best version from the earlier iterations. So this is the most important part. The final model might came from round 142, not round 200, right? Because say you want to train the model for 300 rounds. So at 200 round, the model stopped training because there is no increase in validation. But the model you get is at around round 142 because that's where it has got the best performance. So in summary, we train iteratively, track performance after each step, stop when the validation metrics doesn't improve, and select the model with the best generalization. So this is the most clean, reliable way to improve the robustness of any classification or regression or models on a trained on a structured data. Now let's look at a real world example that brings everything we have learned about early stopping into focus. A customer churn classification problem at our fictional Telnova company. This example highlights not just the technical side of the early stopping but also the business value. So what is the business challenge we discussed in the session number 1? Telnova was facing a common problem in telecom space, customer churn, right? So their goal is to predict which customers were likely to leave, so they could proactively intervene with promotions or customer service outreach. But in a competitive space like telecom, accuracy alone isn't enough. The model also needs to be efficient and generalizable across customers. So the team which implemented XGBoost, a popular gradient boosting algorithm, so they configured run maximum of 200 boosting rounds with early stopping to 15 non-improving rounds. That means if the model didn't improve validation AUC for 15 rounds straight, training would stop automatically. So why 15? It is a practical compromise, gives the model some breathing room to improve but doesn't wait too long if it is done learning. So the model automatically stopped at round number 117 where the validation AUC peaked at 0.88. This is significant because if the team had kept training blindly, they wouldn't have used they would have used all 200 full rounds, but performance would not have dropped because model might have been learned, memorized the training data, and it might have overfitting the data. So the key takeaway is more training does not always mean better accuracy. Without early stopping, the team might have unknowingly shipped an overfit model to production. Now let's walk through the practical code example to understand exactly how early stopping works in real-world classification using XGBoost. In the top, we begin by importing necessary modules. We'll use XGBoost for modeling, train test split from scikit-learn to split the data, and then ROC or AUC score to evaluate the model performance. Then we split our data into training and validation set. This is crucial because early stopping monitor the validation set to know when to stop training. And without validation set, early stopping can't function. It needs unseen data to decide when the model starts overfitting. Then we convert both the training and validation data into D matrix format, which is the XGBoost optimized data structure. It's faster and more efficient for model training. And then we define our model parameters. So we are doing binary classification, so that's why we check object which is called binary logistics. We'll monitor AUC as our evaluation metrics. We have set the model learning rate as 0.1. And if you see on the next line, what we are doing is the early stopping setup. We define list of evaluation sets. In this case, both training and validation. XGBoost will report performance on both at each boosting round. So in the next line, we train the model using XGB.train method with number of boost rounds is equal to 200. This is the maximum number of rounds with early stopping as 10. So training will stop early if the validation AUC doesn't improve for 10 consecutive rounds. So after each boosting round, XGBoost checks if the validation metric improved. If not for 10 rounds tried, it halts and retains the best model it saw earlier. Then in the last line, we use a trained model to predict on the validation set, and then we calculate and print the AAC score, a measure of how well our model distinguish between two classes, say churn versus non-churn. So in summary, this code not only trains a model but also automatically prevents overfitting by using early stopping. So the next concept we'll understand is regularization. Let's first understand what is regularization and why it is very important in building a reliable machine learning model. So just start with a simple analogy. Imagine you're trying to forecast tomorrow's weather. You could try to include every single variable from cloud shape to the color of the sunrise, but doing so might lead you to build a model that fits perfectly on today's data and totally fail tomorrow. This is what happens when a model becomes too complex. It memorizes noise instead of learning useful patterns. So that's what the regularization is, a tool that says, let's not get carried away. Let's keep things simple enough to make sense for tomorrow also. So what it does is it adds a penalty term to the model loss function when parameter like weights or coefficient become too large. This penalty discourages a model from giving excessive importance to any one feature unless it is really required. So for instance, in linear regression, regularization keeps a model from assigning a weight of say 100,000 to something like zip code just because it correlated well in one data set. So at its core, the goal of regularization is to prevent overfitting. Models are often like some over enthusiastic students. They'll memorize everything you give them, but you don't want memorization. You want model to understand the patterns. So that's what regularization ensures, that model captures generalizable pattern, not memorize the training data. So that's why when used correctly, this will lead to a models which are having better performance, and they can perform better on unseen data and also prevents model overfitting. So in short, you get smarter, you have a simpler model that behaves well in production. So it also worth note that the early stopping we discussed in the previous slide and regularization can go hand in hand. They are not mutually exclusive. They are actually complement each other. So regularization acts throughout the training process, continuously guiding the model to be simple. But early stopping monitors the outcome and pulls the plug when the validation performance stalls. So using both together gives you a strong defense against overfitting from a multiple angles. So regularization is kind of a keeping a check on your model creativity. It limits overfitting, it makes a model simpler, and builds a model that you can trust in the real world. So there are different types of regularization techniques called L1 and L2. Let's discuss about L1. So as the top, you can see the loss function. Loss is equal to RSS plus lambda into summation of WI. So the combination of two things. First, RSS is nothing but a residual sum of squares. It measures how well our model is predicting the target. Second, we have L1 penalty. Lambda times the sum of absolute value of the model weights. So what happens here? The model is being told, hey, not only do you need to make accurate predictions, but do it with the smallest set of impactful features. So imagine we are building a model to predict housing price. We got dozens of features: square footage, number of bathrooms, zip code, maybe even something like east facing door. Now without regularization, your model might use everything, even noise. So but with L1 regularization, the model start to say whether for something like east facing door doesn't seems to be helped. So maybe let's reduce the weight of that east facing door to 0. And just like it removes a feature from the equation. So no manual feature selection needed. And let's quickly walk through the benefits of this automatic feature selections, because there is a huge improvement or important, especially in high dimensional data. So it creates a sparse model which are faster, simpler, and easier to deploy. The model is easier to interpret. You are not trying to explain a prediction that relies on 27 tiny coefficients. And finally, it helps fight overfitting by penalizing complex explanations. Think of building model like packing for a trip. So L1 regularization is a wise friend who says you don't need a 5 jacket for a weekend trip. Just pack the essentials. That's what L1 does for your model, and it keeps you the your by keeping the model simpler. It makes sure that the model doesn't become over complex. Now let's walk through simple example of L1 regularization, also known as lasso regression, using a scikit-learn. So in step 1, you can see that in the we first make a regression to create a synthetic regression data with 100 samples and 10 features. We also add some noise to simulate real world conditions. This gives us a playground test how the L1 regularization handles irrelevant or weak features. Now in the step 2, you can see that we are splitting the data into the training, testing using a training test split. So this allows us to train the model on one portion and evaluate it on the unseen data, which is crucial for understanding how well it generalizes. And next you can see that we create our lasso model with an alpha of 0.1. Here is a key idea. L1 regularization adds a penalty to the loss function based on the absolute value of the coefficients. As a result, it shrinks some coefficients to exactly 0, effectively removing less important features. Next, we fit the model on your training data. Behind the scenes, the algorithm is not just trying to minimize prediction error, it is also minimizing the sum of the absolute values of the coefficients. So because of the regularization term. And next, after training, we predict on the test set and evaluate performance using mean squared error. This gives a sense of how close a prediction to the actual values. And then a lower MSE indicates better predictive accuracy. Finally, we print the model coefficient. This is where L1 really shines. You will often see some coefficients are exactly 0. That means that we have effectively dropped those features from the model, giving us a kind of a built-in feature selection which are required. So the next type of regularization we are going to discuss is L2 regularization. So first see the math behind it. So let's begin with the formula. In typical regression model, the objective is to minimize the residual sum of squares. So in other words, how far our predictions are far from actual values, right? So with L2, we modify the loss function to say loss is equal to residual sum of squares, which is RSS, plus lambda times summation of weight square. So lambda is a regularization strength, a hyperparameter we use for model. The weight square is sum of squared weights. By squaring the weights, we penalize large coefficients more aggressively. So encourage the model to keep them small and stable. So the difference between L2 and L1 is that L1 can zero out some coefficients completely, but L2 shrink all coefficients smoothly towards 0 but rarely eliminates them. So this is especially useful when you believe that all the features are useful but none should be overly dominant. Say you are predicting the health of a patient. There could be something like health score you are predicting. You are using heart rate, you are using blood pressure, or you are using oxygen level. They are all relevant. L2 keeps all of them in the model but prevents any one of them is taking over. So this L2 regulation balances the influence of features. Without this, one feature might end up with a huge weight, especially if it is having a high variance or a strong correlation with the target. This can lead to unstable data predictions. So what L2 is doing is they actually gently pulled back some weights, leading to more consistent model behavior even if the data changes a little bit. And this is also L2 is also one of the solutions for the multi-collinearity. So one of the practical benefits of L2 is how well it handles the multi-collinearity. When features are highly correlated with each other, suppose you have 3 features: square footage, number of rooms, and number of bathrooms. They are all correlated because bigger houses have a more of everything. Without regularization, the model might give a huge weight to all of them or behave erratically when one is removed. So L2 helps by distributing importance more evenly, improving model stability and the prediction power. So final takeaway, is that L1 eliminate features, L2 keeps features but keeps them in checks. So when you believe your features are all useful, you don't want to eliminate any of the features, go for L2. Okay, that way you are actually keeping all the features but not one feature dominating others. It is especially useful in health risk scoring or credit risk modeling. So any domain where you can't afford to ignore features, but you still need generalization. For example, in case of health, there is not any medical diagnosis. You cannot afford to lose any parameter. Everything is important, right? So in that case, it makes more sense to use L2. The next concept, which is important concept, is that early drop. So during a training, as a decision tree grows by splitting nodes, that is dividing the data into subgroups based on certain features threshold. Every split is chosen to improve the model objective function, such as reducing error or increasing classification purity. But here is a problem: not every split is useful. Sometimes the improvement in the prediction performance is so small that continuing to grow that branch just adds noise or complexity. This is where early drop helps. Early drop is a type of a regularization technique. It says don't waste time growing a branch unless the improvement or gain is significant enough. Say for example in XGBoost, this is controlled by gamma, a parameter. The gain from the potential split is less than gamma. The tree drops that branch right then and there. It's like saying the idea sounded interesting, but if it doesn't improve the model meaningfully, let's stop going down the road. This reduces the depth of the trees. It simplifies the model and helps to prevent overfitting, all without sacrificing the predictive power of the model. So why early drop is such a valuable technique, especially in real world tree based model? Well, one of the most common problem with the decision trees is overfitting. Trees tend to grow deep and complex, especially if you don't set limits. They'll keep finding splits even for a minor improvement, which often just fit to noise in your training data. Let's say you're building a churn prediction model. Okay, at one point the tree finds that people who use rare mobile browser are slightly more likely to churn, maybe just 0.2% more likely. That's not meaningful, but the tree still makes a split. That one small decision can lead to 10 more branches, and before you know, your model has memorized patterns that don't generalize. So early drop prevents this by stopping the tree from chasing those marginal gains. It is especially useful in a data set with high cardinality features like product IDs or zip codes, or maybe sparse or noisy data sets where many features aren't consistently informative, or wide data sets where trees can get lost exploring dozens of weak paths. So think of an early drops like some type of a gatekeeper at the each of the decision. The gain from the split isn't high enough. It says no, we are not doing this. This helps trees stay shallow, generalize better, and train faster. Now let's see what is the benefits or outcomes of using early drops in your decision tree model. It reduces the tree complexity. With early drop, the model automatically prunes branches that aren't pulling their weight. You end up with smaller, more efficient tree that still capture the important split but don't waste depth on marginal improvement. It improves your training time because algorithm skips low gain branches. It explores fewer splits, which makes training faster, especially in large data sets. Your training tree that focus on signal, not noise. So your model is less likely to overfit to training data and performs better on unseen data. So, and the beauty of early drop is that you can control it with the gamma parameter in XGBoost. A higher gamma means more aggressive pruning, lower gamma more flexible growth. Say in credit risk scoring models in the real world, setting gamma of 10 reduce the average tree depth say by 40% and cut training time by over 30% with no drop in accuracy. That's a huge in a production environment. So early drop is smart built-in editor for your decision tree. It trims the weak branches before they bloat your model. You get cleaner trees, faster training, and better generalization. That's why we have seen that the gamma parameter we have seen in XGBoost model used to control this early drop. So next technique is called elbow method we are going to discuss. So what is elbow method? One of the simple and most intuitive ways to figure out how many cluster to use in a model like k-means. This is more helpful in if you're training a model called k-means, k in a k-NN model, where you're trying to cluster or segment the customers in the different group. When we train a k-mean model, we have to choose k, the number of clusters, ahead of time. But how do we know whether 3, 4 or 10 clusters are the best fit for our data? So you are having, say, large group of customer data, you want to segment them, right? So using k-mean, you need to choose the number of segments or number of clusters, whether it could give some 3 or 4 or 10. So this is where elbow method comes in. We run the k-mean algorithm for different values of k, say from 1 to 10. And for each value, we compute the within cluster sum of square WCSS. This measure how tightly packed the data points are within the each cluster. Lower is better. It means the points are closer to their cluster center. Now we plot this number of clusters with WCSS. Initially, as k increases, WCSS drops quickly because we are adding more cluster to the better fit the model. But eventually the gain starts to level off. Adding more cluster doesn't help much. The point of diminishing returns is called the elbow. So think of it like something like if you're eating some ice cream. The first scoop is amazing, the second is great, by time third time you are happy, but after fourth your joy will levels off. You don't gain much from another scoop. That leveling off point is your elbow. So the elbow method gives you a visual clue about optimal number of clusters where the WCSS stops improving significantly. So next look at another metric, silhouette score, evaluating cluster cohesion and separations. Now that we have used the elbow method to identify a possible value of k, we need to answer the second question. How good are these clusters? The silhouette score gives us that answer by measuring how well each point fits in the cluster, how distinct the cluster is from others. So how it works is that for each data point, it computes the average distance to other points in the same cluster, cohesion. So then it computes the average distance to the nearest neighboring cluster, which is separation. Then it calculates silhouette score using b minus a of max of a and b. Here b is the average distance to the neighboring cluster and a is the average distance to other points in the same cluster. And then by using, if the score is say close to +1, the point is well placed in its cluster. Around 0, the point is on the boundary between two clusters. Negative, the point is probably in the wrong cluster. So this score gives us a quantitative insight into how natural our cluster feels. So for example, imagine you are segmenting customer. If people in the same cluster have behaved similarly and are very different from people in another cluster, your silhouette score will be high. That's good segmentation. In contrast, if clusters overlap or messy, your score will be low, signaling that the data may not be clustered well, or you might have picked the wrong k. Now we need to see like whether we can use both of them together instead of using one of them, right? The elbow method gives us a visual cue, but it can be ambiguous sometimes. The elbow isn't obvious or the WCS drops smoothly without sharp bend. This is where silhouette score comes in. It gives us a quantitative validation, a mathematical measure of cluster quality. Here is how we can use them together. Use elbow method to find the candidate value of k. So if you are for those candidate, calculate silhouette score. Choose the k where you see an elbow and silhouette score is reasonably high. So this helps us to balance simplicity with quality. So for example, you have a marketing data, say the elbow method says size is equal to k is equal to 5, but silhouette score spread it at k is equal to 3. So choosing 3 will lead to a clearer, more distinct segments that well align with your actual customer behavior. So when used together, these tools help us to make smarter decisions, not just about how many clusters to use, but whether those clusters make sense, are they meaningful. So this is especially useful if you are doing customer segmentation, whether you are doing some behavioral analytics, any unsupervised task where interpreting makes more sense, matters a lot. So next concept is stratified k-fold. Okay, so by default, standard k-fold cross validation splits your data set randomly into k subsets or fold, but it doesn't take the target variable distribution into account. Here is what's the problem. Say if you're working on data set where 95% of the labels are 0 and only 5% are 1, with a standard k-fold might put all the ones into one single fold, and now your model is being tested on fold that doesn't even represents your problem correctly. That's where a stratified k-fold comes in. It makes sure that each fold has approximately same proportion of each class as overall data set. So if your full data set has 5% positive cases, each fold will have roughly 5% positive cases too. So let's say you're building a fraud detection model. See, out of say 10,000 transactions, only 200 are fraudulent. That is just 2%. With stratified k-fold, each fold will still contain 20 fraud samples. That means the model trains the realistic distribution. Whether you are doing a training data set or evaluation data set, whether your validation or test data set, each will have the same representation of the fraud cases. That means your evaluation metrics are more stable and representative of the real world performance. This technique is perfectly useful for logistic regression, random forest, or gradient boosting models in binary classification, but also extend well to multi-classification scenarios also. So the next concept we are going to learn is group k-fold. This is the last one. After this, we'll have the next session called evaluating our model. So basically, what is group k-fold? This addresses a problem called data leakage caused by irrelated or dependent samples. So in many real world scenarios, samples in a data set are not truly independent. Say take the case of a retail data set. Multiple rows may come from the same customer. In medical data set, multiple records may be from same patient. In time series or session logs, many events may belong to the same session or date group. If you do regular k-fold or even a stratified k-fold, and some of these related samples end up in both training and validation sets, so you are violating the independence assumption. The result is a data leakage and makes your validation metrics artificially high. So group k-fold solves this by treating each group as a unit. You define a group ID and algorithm makes sure that each group is assigned only to one fold. So imagine you are predicting app churn using a mobile event log and each user has 100 events. If the same user is split between training and validation fold, the model will it cheat the learning by learning from the history, and your accuracy will look much better than it really is. So group k fold keeps each user data contained within the single fold, so that whatever the training data set will not be there in the in the validation or not in the test phase. So you have got true independence, and then prevent the data leakage.